we have UCSD faculty talk. Now it's going to be given by Sean Gao, who is a professor in the Computer Science and Engineering Department, our very own. Sean, the floor is yours.
Thank you. Okay, so well, I have 10 minutes, so I'll do a short and very high-level talk without going into the actual technical details, just to save more time for the guests here. So the title, Optimization and Reasoning, in a perfect world should be a redundant title. The block part is called reasoning. So optimization problems are apparently just subsets of reasoning problems. Okay, so because when you say minimize the function subject to constraints, doesn't matter how complicated they are, and this can be multi-objective as well, right? It's just equivalent to saying, okay, solve this logical formula of finding me an x that satisfies the constraint, and also for any other x, for any other y, you know, as long as you satisfy the constraint, you get better, objectives. And I say this can be multi-objective and arbitrarily complex constraints here, because in that phi you can have, disjunctions and negations, everything. And if you have multi-objective, it's just a disjunction of the f values, right? And then the other side is true as well. Any reasoning problem is an optimization problem, right? So you can talk about arbitrary quantifications, exists for all. And if you just do a translation between, from constraints to sort of the, the energy function that would give you the kind of characteristic function for that constraint, then you can turn reasoning problems into optimization problems. Okay, it just, when you have alternation quantifiers, apparently you have alternation of min and max players, but they are what you can call optimization, right? So these are really the same domain of problems, but two very different communities are speaking very different languages, but live in the same space for a very long time, right? So, sorry, the title is Optimization, New Computing. So these days we see optimization really as the theory of everything, right? So it's clear that AI and machine learning are just applied optimization, right? So it's, if we say physics is the theory of everything physical, then optimization will become the theory of everything mental. And I say that in the sense of optimization and reasoning are the same thing, okay? So when I say optimization, I say reasoning as well. And this is my cat, and these amazing things that we have as our new paradigms of computing, they are truly astonishing, right? So I saw this thing on Twitter that day, and I was like, "There's no way this can work." I took a picture and I sent it to my students and all that, and I was really amazed by what we have, what we can witness these days. Although the success that we're seeing, we've been taking a long time, and a lot of future work needs to be done to actually understand why things happen like this, right? So, in particular, usually you would explain these success by figuring out certain transformations, certain kernel functions, certain spaces where you can come up with a structural understanding of some essentially complex geometries to say, okay, that's why these learning algorithms work, and because following principles of optimization. And then I want to remind you of reasoning, again, same problem. That is the sort of backbone of what people would think of as old computing, right? The fact that we have all these things that may or may not work is because we have decades of effort building all these hierarchies of digital things, right? At the lowest level, you make your hardware, and then when you build code, you need to do your compilers, do your operating systems, and eventually you write complicated high-level programs, and nothing was end-to-end. So we're basically very focused on this end-to-end perspective, but reasoning is a very different kind of type of mindset, right? So it emphasizes more on the sort of the mechanical side of things. So if you think of optimization as sort of a top-down understanding of things, right? So whatever complicated problem, you come up with a giant geometry and then realize things just should do the right thing in that way. A reasoning perspectives have been much more, let's say, bottom up, right? So even the tiniest component in your whole stack requires, well, rigorous and complicated reasoning to make them work. And then you build abstractions around them. Then you have millions of layers, right? That eventually are giving us what actually we can use, right? People think of AI these days as this kind of superhuman, super intelligence, and people talk about safe AI. I mean, I am always kind of cautious about all these calls about, okay, AI safety, blah, blah, because I think people are thinking about AI safety in a very grand interpretation of what we have, right? So, what if it becomes, well, a human killer? And I don't think there are safety issues. I don't want to think about that yet, right? So I don't think we're anywhere near that. But I do care about another type of safety, which is just based on whatever we have right now, what we can get our hands on, right? If we see them as normal technology, sorry, go ahead.
Picture's like 10 years old.
Oh yeah, I know. And you mean this picture?
No, the one on the left.
Yeah, I know. Yeah, and I don't have new videos of the
Those aren't as fun.
Yeah, exactly. Yeah. So yeah, and this picture is 10 years old as well. It's just saying things hasn't improved much. And that. I mean, we have humanoids in our labs. We know. Yeah, I know. Yeah. Yes, I agree. Yeah. So the language model example is, you can take just whatever open model you have, and then based on some things that Misha's lab figured out, you can steer the models to actually give you things that you really don't want to see, right? So these models do contain all those information, and yeah, so you can potentially get all these information from. So I care about the kind of quality of these systems in that sense, right? At that level, just if we really want to put money into it and have customers and all that, can we really depend on them as much as we depend on these projectors? So again, at a very high level, if we do talk about things that we want guarantees or some level of confidence of dependability, the reasoning world figured out this quite a long time ago. There are only two types of things you can ask for a system. Okay, and control theory figures that out as well. We're gonna merge the language. There are only two types of things you can ever ask about any system, right? So think of app as, I know, a robot, a language model, and just forward evaluation of your plain big neural network. You're always doing some transformation of values in whatever space, right? And all those systems, there are only two things you can ask or require. Either you say the bad things should never happen, right? Your car should never hit people, and your language model should then give you social security numbers of arbitrary people. And also, eventually, it should be useful, right? A car that never drives itself is, of course, safe, but you need to do something, right? So you have this duality of things, and in control and optimization, we do know there are ways of doing both of these, right? So, if you want to say eventually good things happen, you want some kind of Lyapunov argument, right? And if we talk about stochastic processes, then it's kind of martingales, super martingales. And in the programming world, in the reasoning world, these are called ranking functions, right? So, which is used to prove termination of programs, which is an undecidable problem in the first place. And then if you want to stop bad things from happening, you basically need to draw barriers that you can make inductive argument about, right? So we do have these basic building blocks in terms of the type of things we need to think about. And my point of talking about sort of the reasoning perspective on this is whatever way of constructing these landscapes for enforcing properties we want, we're essentially talking about an exists for all problem, which is a min-max problem as well, right? So again, I'm just using one language to talk about the story around both sides. So basically, you're always trying to design something, design this process, which is F. And then ideally, if you do care about properties, you want to find this kind of value landscapes or certificates, lambda functions, all of these. And together, they should be able to say certain good things happen over the entire space of your possible inputs, right? Of course, these are things that can be weakened. You can have distributionally robust optimization, for instance, where you put distributions as what you quantify, right? So, but logically speaking, they're talking about this min-max problems for all systems. And what we have been observing is basically, the existential part, coming out with the design and coming out with the model and those things. Surprisingly, we can get away with, a lot of data and probably local optimization methods and some kind of magical way of coming out with the right processes and right structures. But the for all part is always going to be there. Okay, so although this again is still an optimization problem, the for all part requires you to solve a global optimization problem, basically, right? If we think of min-max as this, and usually this value landscape, the certificate that you want, would be extremely non-convex. Okay, and you basically need to think about all the inputs to this V, and also think about the actions on that, and those give you hard problems. And these are the problems that we cannot escape, okay? So we can be okay for some time just being, just seeing promising outcomes from the existential part. We just come up with designs, we come up with ways of figuring out what we roughly want and see great behavior from that. But once we need to put it in a system that everyone needs to rely on, questions about the for all part will come up. And as we see, why are we not having larger models, for replacing our banks, for instance, right? So you could just let it manipulate all numbers just because we have no such guarantees about its reliability. And that's just eventually restricting the applicability of these systems themselves, right? So without answering these for all questions, these global optimization questions, we're not realizing what could be realized, right? So, and if you're now thinking about kind of global organization hard problems over these crazy non-convex functions and blah, blah, many different approaches exist for sure. And, convex optimization for sure is one most important approach to thinking about these, right? So basically, if the problem, even though it's non-convex, as we see from many talks, we can kind of figure out a way of understanding the structure so that we can make some of the convex mechanisms work, right? And then we can achieve global, optimization, sum of squares, for instance. It's a great way of achieving that. And then there will be other approaches as well. There'll be, stochastic or learning ways. You just draw samples and try to come out with an estimation of the thing, and then, do a Gaussian process or whatever. And then use that as your surrogate to kind of answer the questions, right? You can do that, and you can modify the questions so that those give you the right answers according to your definition. But it's dependent on how how high the quality needs to be. But I do want to point out that these pictures we've been okay with them because things have never been so nonlinear as what we have today. Okay, I would say, right? This is sort of the one of the contrived nonlinear optimization benchmark function, right? So it's actually function, and it's sort of it has a good, nice shape. But if you don't do the right algorithm locally, you will have trouble. But even just this function, if you look at a three-dimensional input, right, it will give you this extreme non-convex shape. And, it would be horrible to kind of design algorithm just for that. And this is not, the symbolic form of the function is just there. These are nothing that you cannot come out with, by throwing some positional encoding and some, sigmoids and all that. You can come up with things way more complicated than this. So this kind of very fancy, crazy structure has been there from day one for the reasoning people. Okay, that's why I want to talk about it. Because for reasoning, for discrete problems, there's never been a notion of convexity. Everything is crazy, right? So we have SAS solvers, as we know, that can handle millions of variables, right? So you have these, gigantic exponential spaces. Those are the kind of small structures that you can generate from them. But we do have algorithms that sort of work for them. And then still in terms of theoretical development, there's no real understanding about why SAS solvers work on certain problems. We just don't know. That's been like open for longer than, why neural networks work. And same thing, mixed integer programming and MILP solvers, they've been doing great things for many things, right? Scheduling and all that. And they do a different type of maneuver in these discrete spaces, but you are always dealing with just, arbitrarily non-convex structures, right? You get your solution when you're lucky, and when you don't, when you're not, it just, give up. Okay, so, and then there's Monte Carlo tree search, which has become very popular now, especially for the kind of, language model-based reasoning kind of tasks, and people are starting to talk about it again. But really, it's a method that's designed to explore those combinatorial spaces. So the key difference between the sort of the reasoning approaches and the optimization, or the numerical optimization, and the statistical methods, is really you try to kind of think of everything as growing a tree that you can do backtracking search over, you just hope that you make the right movements in this tree, right? So you can always almost interpret this as a reinforcement learning problem, right? So, but basically everything that involves sequential decision making in this very kind of discrete way would be something that I would call a combinatorial or reasoning approach. So my sort of graduate school work and postdoc work was basically focusing on showing that you can do this. So basically you can take these ideas from, SAS solving and integer programming and do them just for extremely nonlinear continuous functions. Okay, so, it's kind of a naive attempt. So I basically try to just make those algorithms directly work without thinking too much about the complicated understanding of statistical methods or optimization methods that I know better now. But this was shown to be useful for some applications, smaller scale than what I hoped, but they did deliver something. In particular, there's this thing that my group's work was sort of better known in the control and robotic community these days. It's what we call the optimal of control. But I mean, people look at it as saying, okay, you're just learning the Liamo function as with the neural network. What's the big deal? Which is totally true. But we started it really just because we use neural networks just as a particularly useful nonlinear function approximator. And then what we need is to actually solve these exist for all questions with the neural networks in them and with the totally nonlinear dynamics in them. Okay, so you want to find the controller, you want to find the landscape, and then you want to actually make sure that this for all global minimization, maximization is going to work. Okay, so that's actually the core of what we did. Again, it's this game between, you could call a learner and a reasoner, or a minimizer and maximizer, or existential and universal players. But basically, we realized that you can learn these complicated, well, not so complicated from this illustration, but definitely non-convex landscapes and then actually run the reasoning tool, which is dReal, to fully guarantee that this Liammel function works in the domain that we talked about. This is not something you can do with sum of squares. Okay, and Yachen, who's here, did this work, and yeah, and it led to this whole sort of area of neural certificate methods, which is no longer restricted by this capability of solving the for all quantifier now. But you kind of try to have just some reasonable landscapes that you come up with so that you have some understanding of this universal part so that you can do fancy things, right? You can generalize the learning of how to control quadcopters from 3 quadcopters to 1,000 quadcopters, as long as you have these energy landscapes, right? And then you can do imitation learning, not by directly following the trajectories, but by first come out with this landscape and then use this landscape to guide as a more universal thing for other things and all that. And then we have been doing various kind of work on the algorithm part. Nothing I would count as optimization theory or advancing any of the theoretical part in optimization, but it's really just putting different ideas of algorithms together and try to have working algorithms that do better on the benchmarks. So gradually, I'm starting to feel like the old me in grad school feel like there's a way of a perfect combination of these different approaches so that you can have one master algorithm that will solve everything, right? So over the years, I no longer believe in that. I no longer believe that there exists an algorithm that for all problems, you can just solve it. But as my own understanding of these different approaches got better, I do now believe that for any problem, there exists some algorithms that if you understand more about their structures, you will be able to do better with them. So I'm still overall optimistic about these crazy problems and techniques, but a lot of things need to be done. Yeah, overall, I just want to say, we can speak different languages between optimization, between reasoning, and all these things, but I wanted to be more clear these days that, all the technology domains that we have established, right, relies on our ability to answer these hard questions. Okay, so you don't get on an airplane by just seeing demonstration of it, right? So you do need these entire, again, hierarchies of abstractions that build every tiny part with their own exist for all queries, so that you can stack them with confidence, right? And that is what will give us the technology that actually will be useful. When we think about AI, again, the existing part is very promising. It's astonishing, right? But there's a ticking bomb in terms of when we're going to solve the for all part. Okay, so of course, these are not going to be fully precise logical claims. You can talk about things with distributions and all that. You can weaken all these claims in all sorts of ways. But still, the nature of doing something almost global will always be there. And yeah, I think we have an AI summer when we see good candidates for the potential quantifiers, and AI winter comes when we realize the for all part is not solvable. Okay, so not every promising technology became a sustainable industry, right? So as we see how Cruz predicted $1 trillion market and just closed doors a few months ago. So 100 years ago, Hilbert was saying AI will do math. Okay, he doesn't talk about AI. Of course, he's saying basically at that time there's this new notion of computing, right? Everyone is trying to think about to define what algorithms are, what computing is, right? And he's the optimist who's saying, okay, we are going to use these machines to solve everything in math, right? And as we all know, by the work of a lot of logicians and reasoning people, that this is not the case. That there are many questions that we will not know, right? But still, there are things that we just have to know to make certain applications really become a business case, right? So but when we're going to get there, or whether we're going to get there or not, I don't know. And but one way or another, we're going to need to deal with these global optimization problems that we tend to call as reasoning. And yeah, so that's the talk. And then these days, just because I feel my O2 DReal has not been, it's kind of naive, and when I'm not worrying about funding for my students, I do my personal project of doing a new optimizer, so we'll see. Hopefully, in a year, I'll have something else to present. All right, thanks.